after, and then Ines can start.
Okay, let me introduce our speaker today. The Coloquio is Malabika Pramanik. She got a PhD at the University of California, Berkeley. She's a professor at the University of British Columbia, Vancouver, Canada. Her area of interest is harmonic analysis and geometric measure theory. In both areas, she has fundamental and substantial results. So she was awarded with a lot of prizes. And recently, she was appointed as director of the BIRS, the Banff International Research Station. That is a kind of overall hub in America. We are really happy to have you here. And thank you very much for accepting this invitation. So,
thank you, Carlos. First of all, thanks to the Department of Mathematics at Buenos Aires for this wonderful invitation, and to Carlos and Ines for making all the arrangements that made it possible for me to be here today. These are strange times, and it seems a miracle that even through a pandemic, we are able to continue our scientific discussions. And it's only through the goodwill of people like yourselves that this is possible. Just a few words about my talk today. It's a colloquium talk, so I will make absolutely no attempt to go into super specialized area. My only hope is to convey a broad overview of the subject. However, I have listed in my slides a list of references if you are interested for you to peruse. In terms of the format, these are short pre-recorded modules that Ines is going to play. I'm going to be online and keep an eye on the chat window. Every few minutes, once a module ends in about 10 to 15 minutes, we'll take a short break for questions and answers before proceeding to the next phase. Thank you.
Okay.
The title of my talk is Direction and Operators. It refers to a circle of ideas that I have found intriguing for a number of years. There are two main ingredients in this study, the direction and an operator governed by.
¿No se ve el video?
No.
no.
Lo que vemos es
A ver, paren que...
Sorry.
Sorry about that. Just 1 minute. I'll restart. One minute.
Maybe you need to share the whole screen.
Yeah, you have to share the screen and choose the
No, but right now, hold on.
the window where the video is.
Yeah, no, I know, but it's not when I do screen share. Hold on a second. Let's start over. Here we go.
Tenés que cerrar esa ventana.
Okay, now you see it.
No.
Everything white.
ahí está, vemos algo blanco.
Okay, now you see it.
Okay.
The title of my talk.
Oh, no.
Are you seeing it or not?
Just
No.
white.
You should be seeing the video.
No.
Vemos algo blanco, la pantalla blanca.
Is direction and
Okay,
operators.
hold on.
It refers to a circle of ideas that I have found intriguing for a number of years.
Now?
There are two main ingredients in the study.
No.
A set of directions and an operator governed by the set of directions.
Okay, hold on.
It's natural to expect
I'm sorry.
that
about
the
this.
underlying direction set should play a
I don't
role
know where it's
in
playing.
the behavior of the operator. The challenge is to find.
Okay. It's playing in another window. Okay, here we start again.
Sí.
The title of my talk is
Sí, voy.
Direction and Operators.
Alguien dice que a lo mejor se ve en otro escritorio, no en el que vemos nosotros.
I don't know why it's saying that my screen sharing is paused.
Yeah, but we only see the when you open the file, but we cannot see the movie.
Okay. Let me see if I try this.
You have different desktops?
I shouldn't.
Mm.
I'm seeing it all in one desktop, but somehow. Okay, let me see now.
Cerrá la ventana con los archivos cuando,
Okay, no,
cuando empieza. Ahí
Let me-
está.
Yeah,
Ahora sí.
Ahora sí, sí, ahora sí.
Ahora sí.
Gracias.
You see it in full screen, or do I need to make it full screen?
No,
No,
this
it's
is
okay.
It's okay, good.
Ideas that I have found
Okay.
intriguing.
I'll start from the beginning now. Here we go.
The title of my talk is Direction and Operators. It refers to a circle of ideas that I have found intriguing for a number of years. There are two main ingredients in this study: a set of directions and an operator governed by the set of directions. It's natural to expect that the underlying direction set should play a role in the behavior of the operator. The challenge is to find out how.
Por favor.
Here is a plan for my talk. I will start out by describing what I mean by an operator with directions and provide some examples. This will be followed by a discussion about why these operators are important and why we study them. The literature on this is vast. I will try to give an overview of the landmark results most closely related to our study. Finally, if time permits, I hope to give you an idea of some of the proof techniques. Let capital omega denote a set of directions in d-dimensional Euclidean space, where d is at least 2. In other words, omega is a subset of the unit sphere SD-1 in RD. In the diagram, the green globe is the sphere in 3 dimensions, and the red area denotes a possible choice of omega on the sphere. A directional operator takes a divariate function f as input, then uses omega in some way to produce a function g as output. Of course, there are any number of ways in which one can do this. Let me give 2 examples, which will also set the stage for the remainder of the talk. Let f be any nice, smooth input function in d variables. Given a point x in Rd, consider all possible finite line segments that are centered at x and point in some direction little omega in capital Omega. Take the average of absolute value of f over all such line segments. The output function g, evaluated at x, is the supremum or the largest of these averages. The resulting operator, which we denote by capital M sub omega, is called the maximal directional average. Let's try another example. Pick your favorite univariate transform, by which I mean a transformation rule that takes a function of a single variable as input and returns a scalar. For specificity, I have chosen the Hilbert transform on the real line, which simply integrates a function phi of t with respect to the singular kernel 1 over t in the principal value sense. How do we create a directional operator out of this? Given a nice input function f in d variables and any point x, compute your favorite transform for f restricted to a line passing through x and parallel to the direction little omega in capital Omega. For the Hilbert transform, this means considering the principal value integral of the function f x plus t omega as a function of t. As before, we look at the supremum or the largest value of these transforms over capital Omega and call it h sub omega, the maximal directional Hilbert transform. Note that in both of these examples, we have chosen to look at a maximal operator associated with omega. Of course, one could try other ways. For example, average over the points in omega rather than looking at the supremum. However, the maximal operator dominates all such averages and as a result captures the worst case scenario. With these two operators set up, we run into some natural questions. Do such operators actually arise in practice? What properties of these operators are relevant for applications? Are these operators good or bad? And how does one measure the behavior of an operator anyway? For us, an operator is good if it is bounded on certain function spaces, such as the Lebesgue spaces LP. Being bounded on an LP space means that if you feed in a p-integrable function f into the operator, the output function g remains in the same space. Thus, the operator rule does not allow something ill-behaved to be constructed out of a nicely behaved input function. Finally, how does the geometry of capital Omega drive the behavior of the operators m omega and h omega? Just from a superficial inspection, we see that as omega gets larger, we take supremum over larger and larger sets. As a result, both m omega and h omega increase pointwise as omega increases. It seems possible that at some point, these operators may become unbounded for some large omega. Is that truly the case? Before we head out to explore these avenues, let's take a brief pause to see if you have any questions. Thanks. The title of my talk is Directional.
Deja de compartir. Exacto.
This is the end of the first part.
The first part, and I just wondered if there was any questions before we move on to the next.
Yeah.
I have a question.
Yeah.
Can we have omega the whole sphere?
Yes. And in fact, that's a great question, because that's exactly what's going to happen in the very next part of my talk, omega being the whole sphere. Yes.
Sorry.
Great question.
Okay, so if there are no more questions, we can continue with the second part.
Sure.
1 second.
This is the second segment of my talk. Why should we study directional operators? This slide presents a brief sample of mathematical applications where directional operators play an important role. In the fields of geometric measure theory and combinatorics, directional operators are perhaps most well known in the study of sets containing many lines. For example, the Kakaya Besikovic set and its variants. They are the primary tools in many central and often open problems in harmonic analysis. They arise, for example, in Pfefferman's counterexample for the ball multiplier, in Bochner-Ries and Fourier restriction conjectures, and in Stein's conjecture for the Hilbert transform along Lipschitz vector fields. They appear in the differentiation theorems, especially over geometric objects that have orientations like lines, rectangles, and ellipses. Each one of the items on this list is a research direction in itself. For the purpose of this talk, I will restrict myself only to the first one on the list, the Kakaya Besikovic set. In the year 1917, the following problem posed by the Japanese mathematician Soichi Kakaya appeared in Tohoku Journal of Mathematics. What is the least area of a convex set in the plane within which a needle of unit length can turn through an angle of 360 degrees without any part of the needle ever leaving the set? The question was solved shortly thereafter by mathematician Paul, who showed that the answer is an equilateral triangle of unit height. But Paul himself asked a follow-up question. What if the set is not required to be convex? Based on earlier work by Kubota, he showed that the deltoid beats the triangle in terms of area, but there is nothing to show that it is the smallest. Around 1919-1920, the Russian mathematician Abraham Samuelovich Besikovic constructed such a set in the plane with Lebesgue measure 0. His construction permits an easy generalization to higher dimensions. For the purpose of this talk, we will call a set that contains a unit line segment in every direction a Kakaya Besikovic set, KB for short. The history of the KB set is a fascinating one. Besikovic received his PhD from St. Petersburg under the supervision of the famous probabilist Markov. Shortly thereafter, he accepted an academic position and moved to the city of Perm, deep in the Ural Mountains. At that time, due to political unrest in Russia, the university at Perm was completely isolated from the rest of the academic world, and as a result, Besikovic had no knowledge of Kakaya's question. Legend has it that his original goal was to pursue mathematical logic, but the library at Perm did not have enough references on the subject. They did have, however, a great collection in analysis. And in fact, it was a question about multivariate Riemann integration unrelated to the Kakaya problem that led Besikovic to discover the KB set. It was much later, after he moved to the UK, that he found out about the Kakaya problem from Paul and republished his work in the 1940s. Let us ask a delta-thickened formulation of Kakaya's question. If we thicken by delta a set which contains a unit line segment in every direction, what is the smallest area of such a set? In this formulation, a unit line segment after thickening becomes a 1 by delta rectangle. Such a rectangle contains line segments pointing in a set of directions of angular range roughly delta. Can one arrange many such rectangles to cover minimal area, but also cover the entire angular range of 2 pi? I'm going to come back to this diagram in a moment, but let's first give you an actual statement. Besikovic's original construction has been modified in many ways. Let's focus on the version most pertinent to us today. It says the following: fix any positive epsilon, arbitrarily small. Then one can find an integer capital N and a collection of rectangles R1 through Rn, each of length 1 and width 1 over n, and oriented in distinct 1 over n separated directions, such that their combined size is less than the prescribed epsilon. This means that the union of these rectangles, which we call E, is a Kakaya-Besikovic set of Lebesgue measure less than epsilon. At the same time, these rectangles can be arranged in such a way that their reaches are disjoint. What is the reach of a rectangle? So let's refer back to the diagram. Suppose that capital R is one of the rectangles. Let's say this black one oriented horizontally. If we slide R along its long direction by 2 units, so that we get another rectangle of the same dimension and orientation, we call the latter rectangle R star the reach of R. The statement of existence of the KB set says that not only is it possible to ensure that the rectangles Rj have a lot of overlap so that their total area is small, if you slide them 2 units along their respective long axes, their reach rectangles spring apart and become disjoint. So this is all very good, but what does this have to do with directional operators? It turns out that the existence of the Kakaya-Besikovic set has a rather dramatic consequence for the directional maximal average M omega, where omega is the set of all directions in the plane. More precisely, the existence of the KB set dictates that M of S1, the unit circle, is unbounded on all Lebesgue spaces LP of R2 for P between 1 and infinity, including 1, but excluding infinity. How can we verify this? The idea is to construct a LP normalized test function f such that the LP norm of the maximal operator applied to f is very large. Once again, let's fix a positive epsilon, arbitrarily small, and let capital E, given by the union of the rectangles Rj, denote the Kakaya-Besikovic set of measure less than epsilon. E star will denote the union of their reaches. The test function of our choice is the characteristic function of E. This means that the LP norm of f raised to the power of p is just the Lebesgue measure of E, which in turn is less than epsilon. On the other hand, we claim that the maximal operator ms1 of f is bounded from below pointwise by a fixed constant, say 1/10, on the set E star, which remember has Lebesgue measure 1. This means that the LP norm of the maximal function is bounded below by a constant as well. Thus, the ratio of the pth power of the LP norms of the output function and input functions is a constant multiple of epsilon to the -1, which blows up to infinity as epsilon goes to 0. So let's ask then, why is the maximal operator bounded from below on E star? To see this, let's pick a point X in E star, which must therefore lie in Rj star for some j. Let's denote by capital R the tenfold dilate of Rj star. Then R contains Rj, and that is a part of E. Hence, the average of F on R is at least the ratio of the length of Rj to the length of R, which is at least 1/10. Let's pause for a moment to summarize what we have just found. On one hand, the KB set, by definition, contains many lines. And so it can't really be too small, right? But we have just seen that it could have Lebesgue measure 0, and hence is sparse in this sense. So how large is it? Perhaps what this suggests is that Lebesgue measure is too crude a way to assess the size of the KB set. After all, a line and a point in the plane both have Lebesgue measure 0, but they certainly are not of the same size. A line has dimension 1, whereas a point is of dimension 0. What is the dimension of the KB set? Now, there are many distinct notions of dimensions in geometric measure theory. For this talk, we'll just focus on the simplest one. Given a Borel set F, let's cover F by balls of radius epsilon in an efficient way. If it takes roughly epsilon to the minus alpha many balls to cover F as epsilon goes to 0, we say that F has Minkowski dimension alpha. With this definition behind us, let us refine our earlier question about the size of the KB set. Suppose that E is a subset of Rd that contains a unit line segment in every direction. How small can the dimension of E be? The famous Kakaya conjecture says that any such set must have full Hausdorff and hence Minkowski dimension. In other words, there is no Kakaya-Besikovic set of dimension strictly smaller than D. The Kakaya conjecture is known to be true in dimension D equals 2. It remains open in all higher dimensions, though not from lack of trying, as you can see from this list. A number of generation-leading mathematicians have brought a formidable arsenal of tools to the study of this problem, resulting in incremental progress over the years. The references in pink highlight the state-of-the-art knowledge on this problem as of now, both in the Hausdorff and Minkowski sense. Sometimes I find these numbers difficult to digest in real time, so I decided to show you a diagram where things stand. The diagonal line in black is the holy grail of the conjectured bound. The colored lines show some of the improvements. Finally, to round off this discussion, let's ask the following question. We have seen that the existence of the Kakaya-Besikovic set has implications for certain directional operators. Is the converse also true? Can the study of such operators contribute to the study of KB sets? The answer is yes. The two objects are intricately related. Let's consider a close relative of the maximal directional average, namely the Nikodym maximal function. This is the supremum of a function f over all tubes of unit length and cross-sectional width delta containing a point x. The Nikodym maximal conjecture asserts that the operator n delta maps LD to itself with an operator norm that grows sub-polynomially in 1 over delta. It is known that this conjecture implies the Kakaya conjecture. More importantly, any non-trivial LP bound on the operator norm of n delta translates to a lower bound on the Hausdorff dimensionality of the KB set, closing the circle of dependencies between the size of the set and the property of the directional maximal operator. We will return to the talk again in a few minutes, but let's take a short break again to see if you have any questions. Thanks.
Okay, see, somebody have a question or comment, you can also ask directly to Malabika, or you can just write a chat.
I have just a very small question.
Okay.
Here in the Nikodym maximal function, the tubes are in every direction. You don't.
Yes, that's exactly correct.
It goes with the whole sphere, the directions. Okay.
Yes. Yes. In fact, you see, if we let delta go to 0, if in fact then it would reduce to the case of the exact directional maximal average, which we know is unbounded. So thickening it at a fixed scale is trying to retain that feature of all directions, but giving it some volume so that it will blow up, but the rate of blow up contains some information. Okay. It's a more refined version of the directional maximal average. But the tubes point in every direction.
Mm-hmm. Okay. Thank you.
Any more questions? Okay, so we proceed with part 3.
Just a second. I have to. Yeah.
This is the third segment of my talk. Remember our old friends, M omega and H omega, the maximal directional average and the maximal directional Hilbert transform? This section of my talk will provide an overview of some results for these operators, mostly in the planar setting. I have recorded in this slide some of the notable advances in the area for maximal directional averages, M omega. There are many, as you can see. In the interest of time, I will not go over their individual contributions in this talk. Rather, report on the current state of knowledge from this combined body of work. In the previous segment of the talk, we have seen a feature of a Kakaya Besikovic construction that shows a surprising disparity between the size of certain overlapping rectangles and the size of their reaches. Inspired by that construction, we introduce the following definition. Let capital C be a fixed absolute constant. We say that a direction set omega in dimension D admits Kakaya type sets if we can find a sequence of delta going to 0 and a collection of delta tubes of unit length pointing in the directions of omega, such that the ratio of the measures E tilde over E goes to infinity as delta goes to 0. Here, E denotes the union of the delta tubes, and E tilde denotes the union of their C-fold dilates. The same proof that we used before to prove unboundedness of MS1 then lifts verbatim to show that if omega admits Kakaya type sets, then M omega is unbounded on all the Lebesgue spaces LP of RD except L infinity. Here are some examples of sets of directions that admit Kakaya type sets. Of course, the full set of directions in D-dimensional space, in particular, the set of directions on the unit circle is an obvious choice. Another choice is the set of directions in the plane whose angles lie in the Cantor middle third set. This was shown by Bateman and Katz. In joint work with Ed Kroc, we extended this to any Cantor set of positive dimension on a bi-Lipschitz curve in RD. By virtue of our previous discussion, the directional maximal average corresponding to these direction sets are all unbounded. On the flip side, are there direction sets that do not admit Kakaya type phenomena? It turns out there are, and these two have a long history. The first one goes back to the work of Nagelstein and Wenger in the late 1970s. The direction set that they found was of geometric type, namely, each direction vector in the set is parallel to a vector of the form 2 to the minus j1 through 2 to the minus j ad, where a1 through ad are distinct positive numbers. Another such set was found by Carberry, and this one is the default Cartesian product of the set 2 to the minus j. In both cases, the authors show that the corresponding maximal directional average m omega is LP bounded for all p except 1 and infinity. And infinity is, of course, trivial. This means that the direction set omega cannot admit Kakaya type sets. By the way, note that these kinds of geometrically decaying sets are countable with dimension 0, unlike the Cantor middle third set in the last slide, which has positive Hausdorff dimension log 2 over log 3. So let's summarize the discussion so far. We have seen that some infinite but sparse direction sets, such as geometrically decaying sequences, give rise to bounded M omega, but certain denser sets omega do not. This gives rise to a natural question. Which property of omega characterizes Lebesgue boundedness of M omega? The next few slides are given over to answering this question. Of specific relevance to this discussion is the notion of Lacunary sequences. We say that a sequence xj contained in the unit interval is Lacunary if there exists a real number x and a fixed constant lambda strictly smaller than 1, such that the distance from xj plus 1 to x is at most lambda times the distance of xj to x for all j. For example, the geometric sequence 2 to the minus j is Lacunary with lambda equals 1/2 and x equals 0. On the other hand, 1 over j is not Lacunary, neither is the reciprocal of any polynomial in j, nor is the set of rationals Lacunary for any lambda. Of crucial importance to the study of M omega is a property of direction sets called Lacunarity of finite order. In this slide, we'll describe roughly what that means. A set is said to be Lacunary of order 0 if it is empty or a singleton. A set is Lacunary of order 1 if, roughly speaking, it is a Lacunary sequence. A set E is Lacunary of order 2 if it consists of a Lacunary sequence xj, along with a countable collection of Lacunary sequences, the jth Lacunary sequence converging to xj. For instance, the sequence 2 to the minus j would be Lacunary of order 1, whereas the collection 2 to the minus j plus 3 to the minus k is the Lacunary of order 2. Why? Because if you freeze j and let k go to infinity, you have a Lacunary sequence in k converging to 2 to the minus j, which is itself Lacunary. This description is good for building intuition, but it lacks precision. So let's take another pass at the definition in the next slide. The rigorous definition of Lacunarity of finite order proceeds inductively. A set capital E is Lacunary of order 0 if it is empty or a singleton. We say that a set E is Lacunary of order n with Lacunarity constant at most lambda, and we write it in this way: E belongs to capital lambda of n comma little lambda, provided there exists a Lacunary sequence capital X with Lacunary constant lambda, such that for any two consecutive elements A, B in X, the subset of E contained in the open interval A to B is Lacunary of order at least one less. In other words, it belongs to capital lambda of n minus 1. We explain this a bit more using the diagram here. For example, where E is 2 to the minus j plus 3 to the minus k. Here, capital X is the Lacunary sequence 2 to the minus j, and its elements have been noted here: half, 1/4, 1/8, and so on. We have plotted some of the points of E that fall in the interstitial spaces generated by capital X. When restricted to each such interval, E is given by a Lacunary set of order 1. This proves more precisely that E is Lacunary of order 2. So we are now ready to state the main result that we have been working towards. It's the culmination of a combined body of work by several mathematicians, notably Alfonseca, Bateman, Bateman-Katz, and also many others. Let capital omega be a set of directions in the plane. Each unit vector in omega can be written as cosine theta, sine theta, where theta is the angle between the vector and the horizontal axis. We will identify omega with the corresponding set of angles, theta. The result says that the following three conditions are equivalent. Number 1, omega admits Kakaya type sets. Number 2, the angle set theta is not Lacunary of any finite order. Number 3, the directional maximal average M omega is unbounded on the Lebesgue spaces LP of R2 for all P in between 1 and infinity including 1, excluding infinity. I like this result very much. It ties together a number of concepts from different areas. Admission of Kakaya type sets is a measure theoretic property. Finite order lacunarity is a geometric condition. Boundedness of a maximal operator is something we study in harmonic and functional analysis. It seems incredible that all these criteria should contain the same mathematical information. Incidentally, there is a curious dichotomy in this result. If omega is lacunary of finite order, then M omega is bounded on all the Lebesgue spaces LP with the exception of P equals 1. Thus, for example, one cannot have a direction set omega where M omega is bounded for P larger than 3, say, and unbounded for P smaller than 3. There is a P-dependent generalization of this result to higher dimensions by Parset and Rogers. So far, I have only been focusing on the directional maximal average M omega. I would like to compare and contrast it with our second example, H omega, the maximal directional Hilbert transform. This too has been an object of extensive research. I have recorded some of the major contributions to the literature of this operator. I will let you look through this substantial list of work in your own time. Let me quickly draw your attention to some of the results that are known. For example, the work of Demeter and Diplinio shows that if the direction set omega contains capital N elements, then the LP operator norm of H omega is bounded above by a multiple of log n if P is between 2 and infinity. For certain special direction sets, lower bounds are known. This is the case, for instance, when omega is uniformly distributed. A result that I have found especially intriguing is that of Karagulian from 2007 for P equal to 2 and in dimension 2. Later, in joint work with Isabella Laba and our student Alessandro Marinelli, we generalized this result to all P and all dimensions. The result says that if capital omega is a direction set in d-dimensional Euclidean space consisting of n elements, then for any P between 1 and infinity, the LP operator norm of the maximal directional Hilbert transform is bounded from below by a multiple of square root of log n. This result is startling from a number of perspectives. First of all, it says that there is no infinite direction set, omega, for which H omega is Lebesgue bounded. In particular, this means that if omega is an infinite Lacunary set, then M omega is Lebesgue bounded, but H omega is not. In addition, this lower bound of square root of log n is sharp and is attained for Lacunary direction sets. Let's turn now to upper bounds for H omega. I would like to state a recent result in this direction with my postdoc, Jongchon Kim, from 2019. We show that in dimension D, the L2 operator norm of H omega grows like n to the power d minus 1 over 2d up to an epsilon loss in the exponent. Remember, capital N is the cardinality of omega. The bound is sharp and attained for uniform direction sets. Incidentally, we also obtain sharp bounds if omega is contained in an algebraic variety of dimension m. The main takeaway here is the following. whereas Lebesgue boundedness for infinite direction sets omega was the main direction of research for the maximal average M omega. For the maximal directional Hilbert transform H omega, the paramount question is the rate of blow up as the direction set gets larger, subject to certain geometric conditions. Let's take a quick break for questions before we return to the last segment of the talk. Thanks.
Okay, any questions? I think this part was a little bit more technical. Any comment? I think we better go on, and then we have time at the end to.
I have a
more
question. I do have a question, Carlos.
Okay, sorry.
Okay. Are you expecting to have a logarithmic correction to the power that you have in these estimates?
You mean for the plus epsilon?
Yes.
So I think, honestly, that there should be nothing. It should just be n to the power of d minus 1 over 2d. Because I do not know of a single example where there is a lower bound with that power and a logarithmic blow up. So my feeling is that it's an artifact of our proof.
Okay, thank you.
Any other comment, questions? Okay, let's go with more part of the talk.
In the last few minutes I have left, I plan to give you a very brief overview of the proof techniques used in some of the results that I have quoted today. Let's first consider the work of Bateman that resulted in a planar characterization of the boundedness of the directional maximal average M omega. A crucial ingredient in that study was the representation of the angles associated with the direction set of omega as a subtree of a binary tree. What does that mean? I have drawn a binary tree here. The root of the tree, which is also called the 0th level, depicts the interval 0 to 1. At the first level, the root splits into two children. The left child represents the half interval 0 to a half, and the other child is the right interval half to 1. In general, one has 2 to the n vertices at the nth level of the tree. Each vertex represents a dyadic interval of the form k over 2 to the n to k plus 1 over 2 to the n. And if a point x in 0, 1 is written using its dyadic expansion, then the sequence of binary digits of 0 and 1 representing x can be traced as an infinite ray down the tree. In this language, every slope set in the unit interval is given by a subtree of the binary tree, where a ray belongs to the subtree if and only if the point that it represents lies in the slope set. A vertex of a tree is either splitting or non-splitting. A vertex is splitting if both its children belong to T. For example, this here is a splitting vertex. Otherwise, it is non-splitting. So, for example, this vertex, that vertex, and these ones are non-splitting. Here I have drawn in red the subtree corresponding to the slope set 2 to the minus j union 0. For each subtree, Bateman defines a quantity called the splitting number of a tree. How is this defined? First, take a vertex of the tree, script t, and look at an arbitrary subtree of it, called S. Pick out the number of splitting vertices on every ray in script S and look at the minimum of these numbers. Now choose the subtree, script S, for which this minimum is the largest. The resulting quantity is called the splitting vertex, the splitting number of the vertex V, and the largest splitting number of a vertex is the splitting number of the tree. As an example, the red tree here has splitting number 1, since the splitting number of every vertex in the tree is either 0, for example, this one has splitting number 0, or 1, for example, this one. Bateman's insight was that finite order lacunarity of a slope set omega is equivalent to the tree T omega having finite splitting number. This fact played an instrumental role in the creation of a sequence of random test functions that ultimately led to the unboundedness of M omega, where omega is not lacunary of any finite order. What about H omega? The next couple slides contain some proof highlights of our result with Jongchun Kim. One component of the proof is an almost orthogonality principle for this operator. More precisely, let's decompose RD into connected cells OJ, whose union contains omega. Let omega j denote the portion of omega in the jth cell OJ. Let Vj be any point in OJ, in other words, a representative from the jth cell. The set O is the collection of all such representatives. The almost orthogonality principle, this inequality here, says that the L2 operator norm of H omega is bounded above by those of HO and H omega j modulo an auxiliary quantity E that denotes the number of cells OJ that intersect a given hyperplane. Typically, we expect omega j and O to contain fewer elements than omega, and this suggests a divide and conquer strategy based on induction. In order to find an efficient choice of the cells OJ, we appeal to a tool from algebraic geometry, namely polynomial partitioning in Euclidean space introduced by Guth and Katz. The statement is as follows. For any integer capital D larger than or equal to 1, and any finite set omega in Rd of cardinality n, one can find a non-trivial polynomial P of degree at most D such that the zero set of P decomposes the space into big O of capital D to the D many open connected components, each containing big O of n times capital D to the minus D elements of omega. Since omega j contains fewer elements than omega, we can apply induction to estimate the maximal directional Hilbert transform on omega j. But this does give rise to a technical issue. What about the portion of omega that falls on the cell walls? In principle, this set could be of large cardinality, but the key point is that it is contained in an algebraic variety of lower dimension namely the zero set of the partitioning polynomial P. One can then appeal to more refined polynomial partitioning results for algebraic varieties in order to carry the induction forward. Let me close by saying that in today's discussion, we only focused on two directional operators, m omega and h omega. Even within this small sample, we observed a diversity of phenomena in their behavior and in their dependence on the geometric properties of omega. There are a large number of directional operators out there, and their behavior is mostly uncharted territory. It would be of great interest to explore what lies there. Thank you for your attention.
Okay. Very much.
Thank you.
We have some time for questions for the last section and for the whole talk. So somebody have some comment or some question? I have some questions. I'm not sure if it makes sense, but it has been studied, this direction operator for replacing lines, for example, in the plane, by curves or in general for varieties.
Yes, yes, absolutely. So you're even for the original Kakaya Besikovic set was about sets containing many lines. Since then, there has been a lot of work on sets containing many curves or containing many different kinds of algebraic surfaces. There is a lot of work in that direction. In fact, what is also studied is the relation of such sets, the size or the Hausdorff dimension of such sets with maximal operators. For example, maybe the closest relative of this Kakaya Besikovic set with lines replaced by circles. So these are, for example, sets which contain for every point x, a circle with radius somewhere between 1 and 2. So these are sets containing circles of every possible radius. And similarly, there are sets that contain circles with every possible center. And these are, you wouldn't be surprised that these are actually related to circular maximal functions, one of them due to Bourgain, one of them due to Wolf. And one can use such results to come up with Hausdorff dimensions of these kinds of sets. A very wide-scale study of these Kakaya-like sets with curves replacing lines is due to Laura Weiswell. In her thesis, she actually used the theory of Fourier integral operators to study the properties of these Kakaya-like sets containing many curves.
Oh, thank you. Any other question, comments? Well, thank you very much for this wonderful talk. We used to have, in normal times, cookies and coffee after the colloquium.
Okay, I will go and get a cookie then.
We owe you the cookies and the coffee.
Yes, you definitely owe me a cookie. I'll come and claim it sometime.
Okay. I hope the next time you can come and we have a normal colloquium.
Thank you, everyone. It has been a real pleasure and a real honor. Thank you.
Okay. Thank you very much.
Bye.
Bye.